Of the heap allocator?
Sorry?
Of the heap allocator?
No, it's back in the stack stuff.
Okay.
The epilogue after.
Oh yeah, you're still okay. So you're still looking at the frame pointer.
I understand that the common way is they take the EVP and set it to the ESP and move it to the ESP.
Yep.
And then you pop the ESP off the stack, or the EVP off the stack. But does it do anything with it after that? Isn't it the return value, the thing, one more up the stack that it uses to go to the next instruction at the end?
Yes, that's right.
So does it do any, so the idea is you can manipulate that EVP.
Yep.
But at the end of the function, when he pops the EVP off the stack, is there anything that's done with that EVP? Is it?
Not at that point. So think about what happens when the next function returns.
The next, well, if you're in the subroutine, you're going back to whatever called that subroutine.
Yep.
And that's the reference in the, what is that data call, the one right before the EVP?
Yeah, so we'll say that the main function called, the frame pointer function, the vulnerable function. So at the point where you exit the vulnerable function, you will have overridden, you will be controlling EVP, right? Once you're back into the main function, you're controlling EVP.
Okay, so EVP is still, but it's popped off the stack.
Yes, it is. And you're corrupting the least significant byte of that in the vulnerable function.
But when it's popped off the stack, is anything done with that? Is it used as an instruction for the next, for something?
Not at that point, but if you look at the main function, so at that point, it's popping EVP off the stack, okay? And so, and you manipulated that EVP value, so you now control EVP, right? So at this point in Flurry's execution, you have influenced the value EVP.
Oh, so you can, so that EVP will still be there when you call the next subroutine? Is that?
Yes, it will.
Oh, okay.
Yeah.
So you could create your own next subroutine using that EVP and then?
Not like that. So just think that you control the EVP register at that point, okay? The EVP register belongs to you.
Okay.
If you look at the epilogue for the main function, what you'll see is a move ESP EVP. So ESP equal to EVP. Since you control EVP at that point, you also control ESP. Okay?
Got it. So
if you control ESP, you control what gets popped off the stack because you control where the stack points to.
all right.
And the return instruction is basically a pop EIP. So since you control the stack, to control what gets popped off the stack, you also control EIP.
So when something gets popped off the stack, it goes straight into EIP?
Yes.
That's
when a return function happens, it's like a pop in the EIP.
Got it. Okay.
All right, how are my remote people doing? Debbie and Carrie and Butch?
Fine, thank you.
Do you guys have any specific questions or material you would like to for me to go over again before we start with the new material today?
So I don't know if we're going to go over where we're going to start, but I don't really understand why the allocator stuff has any significance to the heap stuff yet, and you're probably going to explain that, but.
So the allocator controls the sizing of the heap. So the memory that the allocator is giving you is coming from the heap, okay? And what we'll see eventually is that by having an overflow in the heap, we can corrupt some of the allocator's meta information it stores on the heap. And by corrupting that information, we can cause our shellcode to execute. And we'll be doing that for the first few hours of today. Okay, so you guys ready to get started? So when we were leaving yesterday, I told you sort of what one of our next things would be, and I'm doing this a little bit out of order with my slides, and it would be trying to cause the heap allocator to crash, or extract the allocator to crash. So I think I talk about this a little bit on, let's see. Starting in slide number 89, and slide number 89 to 91 describes basically the next lab that we're going to be working on, what I sort of slightly introduced to you. And it's basically just causing the, trying to cause the allocator to crash, okay? Because an important thing that you need to be aware of in this class is this right here. This is something I want you to all take away from the class. If the vulnerability is present in an application, if you can gain control of EIP, then you can crash the application, okay? So every time you see Internet Explorer or Adobe Reader crash when you open it, that means that there could be an underlying vulnerability there. And it makes sense, right? Because if you can gain control of EIP and point it at your shellcode, then obviously you can point at some bogus value and cause the application to crash. So when you hear about fuzzing and things like that, basically what fuzzing is just trying to generate as many crashes in an application as possible. And then hopefully one of those crashes will represent an underlying vulnerability. So if there's a vulnerability present, you can crash the application, but just because you can crash an application doesn't mean that a vulnerability is present. The inverse is not true. If you have something like a null pointer dereference or divide by zero, that is likely not exploitable, but obviously the application also will crash on those errors. But if you have a buffer overflow, obviously you can get a crash, and usually you can get control of EIP as well. So with that in mind, we're going to try to crash the memory allocator via buffer overflow. And what we'll find is that we have to position the heap in some way through a series of allocations and deallocations. And then once the heap is organized how we want it, a buffer overflow will corrupt the heap meta information that is stored on the heap, and then eventually we'll get a crash. So we just want to find that crash right now, and then hopefully that will end up being representative of some underlying vulnerability. So let's talk a little bit about the heap layout and what we want to see happen in this lab. So Bill, I'm going to draw some on the board here. We have this file in the alloc directory, which is the lab we're working on right now, called allocuser.c. And the main things we're going to put in allocuser.c are allocations, deallocations, and a buffer overflow somewhere. So we have alloc, some number, then dealloc, chunk, just a little bit clearer. Memory chunk equals allocate some number, how many bytes we need. Deallocate that chunk, mark it as free. And then we'll also have like a buffer overflow in there, because we'll want the buffer overflow to corrupt some heap meta information and ultimately result in a crash. So that's going to be in there somewhere. So it'll be like that more clear chunk, and we'll say like arg v1. Can you guys read that okay? Sorry. Then, arg1 was that first mainline argument like in the basic rule at the beginning. So we're going to have things like this in the allocuser.c. And just to help you visualize what happens is, so this is our heap right here. At the beginning of the execution of allocuser, it's just nothing, right? Nothing's on our heap yet because we haven't allocated anything. Then an alloc comes along, and the user requests 32 bytes or something like that, and a chunk is created on the heap. So there's my, draw over my other stuff. There's my first chunk. And continue to see this, okay, if I have my other line way down here. Okay, so and this is my chunk meta information, right? Remember I talked about at the beginning of each chunk is like available, size, and then pointers, which basically compose our linked list. These are stored at the beginning of every chunk. So we do an alloc, and this is what we get, all right? We do another alloc, and we get another chunk and more meta information. So we'll say this is chunk 1, chunk 2, and then 3. Okay, so here's a question for you guys. Let's assume alloc user did something like this. So we have, I'll just say C1 for chunk 1 equals alloc C2 equals alloc. All right, so this is what my heap is looking like based on the source code here. This is what would be happening to the heap. C3 equals alloc. Now, if I do a buffer overflow in the second chunk, so we'll say string copy C2, then, data. If I overflow C2, where will my overflow go?
Meta chunk 3.
Yes. So what is different about this? So if I had an overflow in chunk 2, like Rob just pointed out, it would go blah, 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 overflow, and it would destroy chunk 3's meta information, okay? All this would be over in like 41, 41, 41, 41, and it would probably even go up into here somewhere. So what's weird about this is that an overflow here basically overflowed blah, 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 and clobbered this thing. If this was a stack, it would have been the other way around, okay? If these were stack variables, if I overflowed C2, imagine these are just local character buffers, C2 would have overflowed C1, and that's because the stack grows down and the heap grows up, right? So just keep in mind when you're working on this lab, an overflow in C2 is going to overflow this guy, and this is what the heap looks like. So I just want you guys to visualize that. However, if you put alloc, if you put this in alloc user.c and did an overflow, you probably wouldn't get a crash, just because we haven't sufficiently corrupted the heap yet. So what I want you guys to do is play around with the alloc user.c file and do something like this with a series of allocations and then a buffer overflow. And then I'll go ahead and give you a hint. You're going to have another heap operation here. And I won't tell you which chunk it will be on. Obviously, you want to do a heap operation affecting one of the chunks that has corrupt meta information. And you want that after the buffer overflow, the next heap operation to do, which is either an allocate or a deallocate, right? There's only two operations you can do. Either allocate or deallocate on some chunk here will cause a crash. And I want you guys to play around with, a series of allocations and deallocations to order the heap in some way so that you think after you do a buffer overflow and you corrupt some heap meta information, you'll be able to cause a crash by doing the next allocate or deallocate will cause a crash. Yeah?
Are we supposed to use the standard malloc, or are we supposed to use your...
No, just use my alloc. Yeah. So one thing to keep in mind as well is that, let's just draw the heap again, just to help you guys visualize what's going on and what is possible with the heap. Let's say my alloc user over here, so you guys saw that. Let's say my alloc user does C1 equals alloc 10, 1 and 10 bytes, okay? So, same as here, chunk 1 is created. My heap looks like this. Get rid of this. So in alloc user I do C1 equals alloc, 10 bytes. This is what my heap looks like. We all follow that, right? Makes sense? Then I do dalloc C1. My heap at this point still looks like this, except a bit is set in here to say this is now available. Available equals 1. And it's on the linked list now too, okay? So this is what my heap looks like. Now, if I do C2 equals alloc 10, what does my heap look like now? Anyone tell me? Yeah.
It's exactly the same.
Exactly the same, because it would just reuse chunk 1, okay? It would set available equals 0, but the heap would still be the same. So if there's an overflow below this, it might have corrupted this information and caused problems, but for now, everything is okay with the heap, so I do this allocation, the heap stays the same because it reuses chunk. But let's say we do C2 alloc 20, then what would the heap look like? Then, yeah, that would just go up, right? I'd have to create another chunk. So, now that you can visualize what is happening with the heap, I want you to do, this series of allocations and deallocations and a buffer overflow. And then, with the next heap operation you do, allocate or deallocate, I'll tell you which one, you should get a crash. And I want you to play around with trying to discover how to make that happen. It's all about structuring the heap in the right way so that when you perform the buffer overflow, you corrupt what you need to corrupt and cause the crash. You see this a lot with heap vulnerabilities. The attacker has to do a lot of stuff to organize the heap in just a special way so that the vulnerability can be exploited. Yeah?
A question about the pointers. Does that point to any location in memory, or is it just areas that are confined to where the heap is?
Yeah, it points to the next in the previous free chunk. But if you do an overflow, like if you overflow chunk 1 into chunk 2 here, you could corrupt those pointers to point out whatever you want to point out. And that's important. Yeah?
With the deallocator, calls your defrag heap thing, does that significantly change the linked list? We're to where, chunk 2 is not necessarily contiguous with chunk 1?
They are still contiguous. Okay. It does change the heap, but it like rewrites all the heap meta information, but everything is still contiguous. It doesn't change the order of anything. So I want you guys to play around with that for a little bit. Just try to get the good old segmentation
Corey?
fault to happen.
Maybe
Yeah.
my C's a little rusty, but I'm looking over the allocuser.c file, and
Yeah.
I'm trying to understand exactly where the input's being used that the user provides.
Okay, let me show you on the screen here. So if you see this str copy right here, yeah, the argv1, this is actually like the first command line argument passed to the program. So if I ran the program like alloc user ABCDEF. ABCDEF is what is argv1 at that particular point in time. So it's basically just like the argument you're passing to the program.
And is that coming in through the char argv?
Yes. Exactly.
But we're not passing in an int argc. Is that correct?
That is implicitly passed in by the operating system. That argc equals how many command line arguments were sent to the program. Like in this case, it would be 2, and that's because it implicitly counts the program name as the first argument. Okay, so 1, 2, and if I added another argument like second arg, it would be argc would be equal to 3, and so on.
So
all you have to know though is that argv1 is equal to whatever you pass as the argument for alloc user. So if I was instead to make this like Perl E print A times 1024, it would, you know, replace that with 1024 A's and, you know, overflow that sub1 buffer.
So what makes this code quote unquote crappy is the fact that you've made that hard allocation to buff1 without any checking.
What makes?
So you've limited it to 128, but you've done no checking to make sure that what I pass you doesn't exceed 128.
Yeah.
Okay.
Yeah, exactly.
Troy, we have to use GCC for the
Use GCC, yeah. You could technically use ECC, but just use GCC because you'll need it later for returning this into a real exploit.
what's the argument to get plug holes, so basically stuffing it for sort of GCC.
Oh, to compile it, you mean? Okay, so to compile a program, do GCC.
The build script.
Oh, yeah, there is. Yeah, if you just do, have to do that, yeah. So you can modify alloc_user.c, don't modify alloc.c. In the real world, that would be like a DLL or a shared library, but it's kind of a pain to compile things into a shared library anyway. So oh, also, if your screen gets messed up with the colors and all that, you can just type reset and hit enter. And it'll fix the colors. So for instance, I'm going to make an attempt here at making things crash. You know, I did this first one with just creating the buffer and doing a string copy and a deallocation, and it didn't work. There was no crash. You know, I built this, and if I try to crash it, so, okay, that didn't work. Maybe if I add in another chunk, so like char 2 equals alloc 128. And then, so now I should be corrupting chunk 2's meta information, right? Because I'm overflowing buff 1, it's going into buff 2, maybe that'll cause my crash. Still nothing. I want you guys to mess with it a little bit right now before I give you too many plans.
For a dealloc, so that does not modify the structure of the chunks. It just modifies whether they're the flag or whether they're free or not.
It does not modify the order of the chunks, no, but it does modify some of the chunk meta information.
only the free flag?
No, it actually, because remember I said the deallocate is kind of dumb and just rebuilds the whole heap. So it will actually reset all the chunk meta information. That's the right question to ask. You're thinking along the right path.
But the meta information is the availability and the size, right?
And 2 pointers.
But, okay. But you said the pointers are always going to be the same. It's going to point to the next one and the previous one.
Yeah.
And those are always. It's what I meant is, do you ever like during deallocate? Does it ever short circuit a pointer to, instead of pointing to that next one, it points to a different one for some optimization reason?
Yep.
But the only metadata that deallocate should, according to what you said, would be the availability, because it's still going to point to the next one and the previous one, and the size is going to be the same, right?
Yeah, that's technically what it should do, but it does change other stuff, just because that was easier from an implementation standpoint. So just keep in mind that whenever you do a deallocate, it is going to, let's say you do a buffer overflow here. So I overflowed chunk 1, this is chunk 2, and I blew away that information. If I was to do a deallocate, it would actually repair all this meta information. All this would be repaired thanks to the. So obviously, deallocate is probably not the heap operation that's going to cause the crash. It repairs everything, right? Which leaves only one other contender in the arena for what's going to cause the crash. And so something to think about is that you know at this point that the crash will happen during an allocation. All right. And in the chunk meta information are 2 pointers that you can potentially corrupt during a buffer overflow, the previous and next pointers. So you can corrupt those, like in the picture I drew here. This is chunk 2. Overflow in chunk 1 corrupts chunk 2 and its meta information, including its next and previous pointers. So I can say I have an overflow here. Next equals 41411. Previous equals 4141. If I was to do a deallocate, those would be repaired. What I want to force the allocator to use those corrupted pointers somehow. All right? So think about how to do that. How can I force the allocator to chew on these pointers that I've corrupted? And to know how to do that, you have to understand how the heap allocator is working. So play around with it again.
Go back to the previous screen.
What was that?
Can you go back to the previous screen?
Yeah.
Right there. Please.
All right, so Dave, why don't you tell us, as a hint to the other students, did you overflow, what type of chunk was it that you overflowed that inevitably led to the crash? Was it a free chunk, an allocated chunk?
Yeah, an available chunk. Free.
Yeah, so it was a free chunk, all right? And the reason he used a free chunk is because he wanted those corrupted pointers, the next and previous pointers, to be used. And those are only used when the chunk is on the free list. either Josh or Dave tell me what is the exact function in the memory allocator that the crash is occurring in?
No.
Is it unlinked chunk?
Yeah. And so what is that function responsible for? It is responsible for removing the chunk from the free list, from the linked list of free chunks.
So it's in the process of redirecting the
Yes.
pointers
Yep.
and the adjacent
Yeah.
nodes in the list.
So Bill, I'm going to draw something else on the board. What the unlinked chunk function does, whenever you have a chunk on the free list that the allocator is going to reuse, it needs to remove it from that linked list of chunks. So let's imagine our linked list is like this. These are my chunks. And then this is the free list of chunks. Then I have these forwards and backwards pointers in each of them, right? So let's assume that this is what the heap looks like, all right? This. Let's just assume that we're talking about the free list, and I have an overflow that ends up corrupting this free chunk right here. So this chunk was free, and overflow comes over and totally destroys the next and the previous pointer. We're set to like 41, 41, 41 now. When we do an unlinked chunk operation to remove this from the linked list, what we do, and this is common like linked list deletion functionality, is we make this point to this, and this point to that. So we basically just like are making the pointers jump around that way. The way that you actually do this in C is you do something like, we're unlinking this from the linked list. We would say like this next pointer, previous pointer. So this guy's previous pointer, let me draw my original diagram here.
I guess I didn't.
So next pointer, so this chunk's previous pointer equals previous pointer. And if you look at the unlinked chunk function, you'll see it's doing something similar to that in the alloc.c file. So this line right here would say next pointer, previous pointer, so this guy right here equals previous pointer, so basically points over here. And then it would say previous pointer pointer equals next pointer. And that would basically say this guy's next pointer all the way to that. And that sort of removes this from the linked list, from that free list. And so when you corrupt this chunk, both of these are set equal to AAAA 401. So 414141 equals previous pointer, and then 41414141 equals next pointer. And since 414141 is a bogus address, that's why you're getting that crash. Yeah.
I think I got it.
Okay. Did what I just described make sense? Okay. So the linked list only points to free chunks of memory. That way when an allocation occurs, it can traverse that linked list and see where my free memory blocks are and see if any of them are big enough to satisfy the user's allocation request. So I'll start working out on my screen, like what you should do to get the crash. Okay, so with the source code I have up here now, I create two chunks of memory on the heap. Chunk 1 and chunk 2, right? Two chunks of memory allocated on the heap. I mark chunk 2 as free. Okay, so I still have two chunks of memory on the heap, but I have now one on the free list, and its available bit is set to 1. I overflow chunk 1, which overflows into chunk 2, all right? This corrupts all of chunk 2's meta information, like its pointers and so on. And now, if I do, I'll throw a curveball, you guys. Would this cause a crash?
No,
Why not?
because buff 2 is open, but it's not going to be used.
Right, because it's too small. Too small. It won't. Yeah, it would traverse. It would try to traverse this linked list at least, and it would say that, look, the size isn't big enough, so I'm not even going to like consider this.
Doesn't that bring a written zone?
Could you override your size?
Yeah. So in this case, it would not cause a crash though, because it would successfully get to this chunk just by way of the uncorrupted beginning head of the list. So like the initial pointer. But I guess if you override it with 414141, it might still cause a crash. So yeah, actually I'm not sure. So
Yeah, it depends on what you pass in as a.
yeah, it depends actually. Just to be more clear, let's put it at 128. So this would definitely cause a crash because you've corrupted all this chunk's meta information, and the allocate algorithm is going to try to parse that corrupted meta information when it's traversing the free list. And it's going to see, when it tries to use those next and previous pointers, it's going to crash on that, basically the unlinked chunk function, like I showed you on the board. Now, does everyone follow why
Do you
this
need
is,
to do you need to
would eventually cause a
deallocate
crash? Does that
buff
kinda make
2?
sense to you
Would it
guys?
still not?
Right. Yes, yes. If you did not deallocate buff 2, this would not crash because the allocate algorithm would not even consider, would not even look at the corrupted chunk because it would not be on the free list. The allocate
So
algorithm
I'm
is
wondering
only
the way it
gonna
is
look at the
there
chunks
now,
that are on
though,
the
when
free
you
list.
added the new alloc for buffer 3, if we could get rid of the dealloc buffer 2, and it would still look and see that it was corrupted.
It would not.
Okay.
So let's assume that I did not deallocate this. Okay? So what we would have at this point is, I'll draw on the board actually. Okay, so at this point, let me get rid of this corruption here. This is good. metadata, meta. Okay, so 2. So we've allocated buff 1 and buff 2, right? So the heap looks like this. We have 2 chunks of memory, chunk 1 and chunk 2. And we do an overflow in the first chunk with that string copy into buff 1. And what that does is it goes A, you know, blows all this away. Chunk 2's meta information is bad. We'll say this is A's now. But then we come along and we say char buff 3 equals alloc 128. We invoke the allocate algorithm and it says, okay, the user just requested 128 bytes. Let's see if I have any free chunks that I can serve back to the process. And it says, no, actually I don't, because nothing is on the free list of free chunks because nothing has been deallocated. So my heap is totally utilized. So I just have to do this.
Okay, so it doesn't read the metadata. Doesn't read the metadata when it assigns a new. When alloc runs, it doesn't read the metadata again. It just looks on the linked list of what's free.
It will only look at the metadata for what is on the linked list. And in this scenario, what you were describing, without that deallocate, nothing is on the free linked list. So that corrupted, that information will never be used.
I had the same question, and
Yeah.
what I had previously thought was that the linked list was the actual metadata structures linked together. But the linked list is a separate data structure elsewhere.
So yeah, a little bit confusing. You just have to remember that only the free chunks are on the linked list. Because there's no use looking at the already allocated chunks when the allocation algorithm happens, because you can't reissue an already allocated chunk to the process. So to make it faster, you only want the free chunks to be on a linked list. That way you're only looking at free chunks whenever an allocation happens. That way things happen more
so
quickly.
when you invoke dealloc, then it has to read the metadata, I guess. Just to zero it out, if nothing else.
Because then, yes. Okay. So, what we're going to do now is we got a crash, and I have told you guys if you can crash it, you can maybe hack it. So that's kind of the first step in the exploitation process. But like I've also hinted at, we'll get into a scenario with this heap overflow where we can arbitrarily change 4 bytes of memory. And if you can arbitrarily change 4 bytes of memory, you can obviously change the return address, but there's also lots of other more reliable things you can change to gain control of the instruction pointer. And we're going to do a little mini lab where I give you a program which will change any 4 bytes of its own process that you tell it to. And we will try to leverage that to get our shellcode to run. Before we do that, why don't we take like a 10-minute break, just so you guys are fresh for that.